when we deal with two variances or standard deviations, for the comparison of two variances or standard deviations, we use what's called an F-test, like chi-square. It is non-symmetric, it is skewed to the right, and it is important not to confuse it with the chi-square. In the case of the chi-square, we are dealing with a single sample. In this case, we are dealing with two. The values of F cannot be negative, remember, just like chi-square. The distribution is positively skewed, the mean is approximately 1, and it's a family of pairs based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the variance of the denominator. So the degrees of freedom for what we have learned so far, there was one of them. Now we have two of them, one for the top, one for the bottom. It's known as degrees of freedom df1 for the numerator, df2 for the denominator. Now, this is what I want to emphasize. In some text, the larger of the two variances is placed in the numerator regardless of the subscripts. In others, this is not the case. Therefore, follow what the text or author wants you to do. I want to elaborate on that because I want to make sure everyone understands what we are trying to say. In many texts, they make sure because of the limitation of the table, it's right-tail test, and the larger variance is chosen to be the first group, so it's S1. But it may not be the case in others. We try to make it right-tail test. In some cases, it's left-tail test or even two-tail test. So pay attention to what you're dealing with. Because F-test is absolutely simple. Simply F is S1 squared over S2 squared. So it can't get any simpler than that as far as the test statistic goes. And many authors want to make it nice and easy by choosing S to be larger for the top one. Let me show you the table before we actually move on. So here's the table. Look at the F table. First, you need the area, so alpha. And then you need the degrees of freedom for the numerator, known as df1, which is at the top. The numbers at top represent degrees of freedom for the numerator. And then the numbers in the left column would be df2, or degrees of freedom for the denominator. As you can see, the top, for example, ends with number 10, and then we have F10 here, then this is fine. And by the way, alpha is 0.05, as you can see. Then I have another one for you. You can look this up, even you can Google search these tables. Alpha is 0.05. We have degrees of freedom of, as you can see, goes all the way to 10, and then it jumps to 12, and then 15, and 20, and so on and so forth. So it basically is a limited table, and you can move on with that. Take a look at what comes next. This is what I want to emphasize. Alpha is different now. You have a different table. That's how limited this F distribution is. So not only you have to pay attention to degrees of freedom of the numerator and degrees of freedom of the denominator, you also have to pay attention to the choice of alpha, so you use the proper table. So for every alpha, we have a different table. So I'm going to look at another one. This is alpha of 0.025. And look, now we have alpha of 0.01. So I hope it is clear that this is simply because the table is extremely limited. But how do we look it up? It's very simple. You first and foremost choose your alpha. Then the degrees of freedom of the numerator is the top row, and the degrees of freedom of the denominator is the left column. And let's start with a simple example. So we want to find the critical value for a two-tailed test, F-test, with alpha of 0.05, when the sample size from which the variance for the numerator was obtained was 21, and the sample size from which the variance for the denominator was obtained was 12. As I said, we normally look at the case which is a right-tailed test. Now, if alpha is 0.05, then you got to look up alpha equals 0.05, except this is a two-tailed test, everyone. And alpha must be cut into two pieces, 0.025 on the left and 0.025 on the right. Now, if you choose such that the larger variance is at top, then all you have to do is look at the right tail test and compare it to that F and make a decision. That's the idea behind it. That's why. And so we have the following. Alpha is split. Okay, normally it's a right tail test, remember that? Since we try to use F larger than or equal to 1. It's a two-tail test. Alpha is 0.05. Cut it in 2, you get 0.025. Now, when you go to the table, the DFN, degrees of freedom for the numerator, and at this one we call it DF of numerator or DF1, DF of the denominator or DF2, depending on the text. They may specifically say DF of numerator and DF of the denominator. They may say DF1, DF2, as you saw from the table. So, first and foremost, the table you got to choose has to be alpha of 0.025. Now, the degree of the freedom for the numerator is 20 and for the denominator is 11. So take a look at what's going to happen. So as you can see, the top is limited, but number 20 is there. So you look for number 20 in the top row, you look for number 11 in the left column, and you basically put them together. So that's 20, that's 11, and the number we see is 3.2261. And this is what we have as CD or critical value. For as long as we have the table in front of us, we can easily do the reading. And the very first thing, we choose the proper alpha. Most of the time, alpha is 0.05, and most of the time, it is right tail test.
Find the critical value for a right-tailed f-test when alpha is equal to 0.05. The degrees of freedom for the numerator, abbreviated DFN, are 15, and the degrees of freedom for the denominator, DFD, are 21.
As you can see, alpha is 0.05, so that's the first thing we look at. And because it's a right-tail test, then we need alpha of 0.05. Just for the sake of argument, if it were left-tail test, then to the right is 0.95. They don't have anything like that as far as the table is concerned. Okay. With that being the case, we don't have to subtract 1 because degrees of freedom are given. So it is a right tail test. Alpha is 0.05. We use the 0.05 table. Degrees of freedom of the numerator or DF1 is given, and DF sub D or DF are interested in finding the area of 0.05, and we are interested in using this table, DFN, which is DF1, so this is DF1, then we just say DF2. So you look up that number, it happened to be 2.18 or 2.1757. So two variances or standard deviations.
The f-test for testing claims made about two population variances or standard deviations. The f-test named for statistician Sir Ronald Fisher uses the f-distribution introduced in this section. The f-test requires that both populations have normal distributions. Instead of being robust, this test is very sensitive to departures from normal distributions, so the normality requirement is quite strict.
The bottom line is, because of the limitation of the f-test, it must be normally distributed.
Conduct a hypothesis test of a claim about two population variances or standard deviations. Any claim made about two population standard deviations can be restated by an equivalent claim about two population variances. So the same procedure is used for two population standard deviations or two population variances. 1, two populations are independent. 2, the two samples are simple random samples. 3, each of the populations must be normally distributed regardless of their sample sizes. This f-test is not robust against the departures from normality, so it performs poorly if one or both of the populations have a distribution that is not normal. The requirement of normal distributions is quite strict for this f-test.
You are dealing with the same concept as you've been before. SRS, independent, normally distributed. In short, simple random sample, they must be independent, they must be normally distributed.
Critical values. Critical F values are determined by the following. The significance level alpha F distribution tables includes critical values for alpha S, such as alpha equals 0.025 and alpha equals 0.05. 2. Numerator degrees of freedom. N1 minus 1 determines the column of the table. Denominator degrees of freedom. N2 minus 1 determines row of the table. For significance level alpha equals 0.05, refer to the table and use the right tail area of 0.025 or 0.05, and depending on the type of the test, as shown below. For a two-tailed test, use the table with 0.025 in the right tail. The significance level of 0.05 is divided between the two tails, so the area in the right tail is 0.025. For a one-tailed test, use the table with a alpha equals 0.05 in the right tail.
So let's start with one example.
The standard deviation of the average waiting time to see a doctor for non-life-threatening problems in the emergency room at an urban hospital is 32 minutes. At a suburban hospital, the standard deviation is 28 minutes. If a sample of 16 patients was used in the first case and 18 in the second case, is there enough evidence to conclude that the standard deviation of the waiting times in the first hospital is greater than the standard deviation of the waiting times in the second hospital? Alpha equals 0.05.
And so here's the given. I think it's very straightforward. We are dealing with two groups, and we can see that we are given with SRS. Urban has a sample size of 16 with S of 32. We call him N1 and S1. And suburban, N sub 2 and S sub 2. Notice, when it's up to you, when you have a choice, you choose it such that the first one has a larger variance, larger standard deviation. But again, if it's given to you differently and you are following that, so be it. If it's up to us, we make sure it's right take this. It's a good practice to have a larger variance or standard deviation for the first group. Alpha is 0.05. That means when we want to look up that table, use the table with alpha 0.05. That's for the F distribution. And so how do we write H0 and H1? You use this one. However, if instead of that you use this one, then you should use this one along with that. It has the same meaning. Whether we say sigma 1 squared equals sigma 2 squared, or sigma 1 squared over sigma 2 squared equals 1, is the same thing. We say sigma 1 squared is larger than sigma 2 squared, or sigma 1 squared over sigma 2 squared is larger than 1. It is the same thing. If we use this one, we say sigma 1, this one, and it's important to know not to use all of them. You use just one of them. Any of them, in this case, because it's referring to standard deviation, perhaps the third one is the best choice. Now, what is the test statistic? S1 squared over S2 squared. So this is a right tail test. S1 squared over S2 squared. And you get 1.3061. So now, degree alpha is 0.05. This is a right tail test. Degrees of freedom of the numerator is 16 minus 1. And the denominator is 18 minus 1. So looking up the table results in the following. So this is 0.05 and this is 2.3077. So where is the test statistic compared to this number? It's somewhere in the non-rejection region. Therefore, the result is 1. Fail to reject H0 or do not reject H0. So if you are not rejecting H0, you're rejecting H1, which contains the claim becomes false. So, do not reject H0. The claim is false. There is not sufficient evidence to support the claim that the standard deviation of the waiting times of the urban hospital is greater than the standard deviation of the waiting times for suburban ones. If technology is used, it gives us the p-value. So for technology, namely TI, you just use 2 sample f-tests. You plug in the information, and as you can see, the p-value is larger than 0.05. Here's the next example.
A medical researcher wishes to see whether the variance of the heart rates and beats per minute of smokers is different from the variance of heart rates of people who do not smoke. 2 samples are selected and the data are as shown. Using alpha is equal to 0.05, is there enough evidence to support the claim?
We are dealing with 2 samples, and we're going to start writing the very first step, H0 and H1 as follows. H0 sigma 1 is equal to sigma 2 squared, and H1 sigma 1 is not equal to sigma 2 squared. since alpha is 0.05, it cuts the alpha into two equal parts, making up two tails. The left tail and the right tail is 0.025. And so if you want to think of it as a right tail test, you can, if you choose the first group with the larger S, which is 36, and you're going to do that. So test statistic is S1 squared over S2 squared. Plug in. And bear in mind that S1 squared is given, not S1. You don't have to square it. It is given in that form. In other words, variance is given. And so that would be the test statistic. Critical value, alpha is 0.05. You cut it into two pieces and you use a table of 0.025. Degrees of freedom of the numerator is 26 minus 1. For the denominator is 18 minus 1. Now, when you go to the table, the limitation of a table, for the numerator, we stick with whatever we have. If we have 25, fine. If not, in this case, 24. And we get the F, 2.56 roughly. So notice the area is 0.025. Now, where is test statistic? So when you look at test statistic, it's way into the rejection region, where you reject H0. Because you're rejecting H0, you're loosely put you're accepting H1, the claim becomes true, and you know the rest. So, reject H0, the claim is true, there is enough evidence to support the claim that the variance of the heart rates of smokers and non-smokers is different. Here's another one.
Listed below are stats for student evaluation scores for courses taught by female professors and male professors. Females, X bar 1 equals 3.8667, N1 equals 12, S1 equals 0.5630, males, X bar equals 2, 3.9933, N2 equals 15, S2 equals 0.3955. Use a 0.05 significance level to test the claim that course evaluation scores of female professors and male professors have the same variation.
So all we have to do, just write different steps. The very first one obviously being H0 and H1. H0, sigma 1 squared equals sigma 2 squared. And that is the claim. Okay, use a 0.05 significance level to test the claim that the course eval scores of female professors and male professors have the same variation, have the same, that is the claim. And not equal makes a two-tail test. So test statistic, S1 squared over S2 squared. Plug in. Notice we need to square them. So I want you to pay attention whether the variance is given or standard deviation. In this case, standard deviation is given. You must square both numbers. What about the critical value? If you want to go with the two-tail test, you have to go to the table with alpha 0.025 because you divide it into 2 and you get 0.05 divided by 2 equals 0.025. Degrees of freedom of the numerator is 12 minus 1, denominator is 15 minus 1. And again, I've shown you the table. You're more than welcome to explore that on your own. Limitation of a table, you get numbers in between. 3.1469 and 3.050. Now, what matters is that clearly when you do the drawing, take a look at what happens as far as the drawing is concerned. You have the upper one with a 3.0946. This is from technology. The lower critical value, 0.2977. This is from the technology. Now, even with the table and without the technology, the number 2.0269, it's clearly less than both numbers that you pick up from the table, which is way into the non-rejection region. So you should have no problem making a decision according to even your calculation, and you're looking at the table, the limited table that you have to give. You get the right decision, which is not to reject H0. Do not reject H0, fail to reject H0, however you want to put that. So if you're not rejecting H0, then claim comes with it. You're not rejecting the claim becomes true, and you write the rest of it. There is sufficient evidence to support the claim equal standard deviations. This is a short way of writing it, or you can write the whole thing. There is sufficient evidence to support the claim, and then you pick up a sentence from the question. The claim that course eval scores of female professors and male professors have the same range. You can write that down. Now, I want to discuss the p-value, and that would be the area to the right of the test statistic. And if you want to go with the two-tailed test, you have to multiply it by 2 values. So as far as the test statistic goes, we got this number. So this is your p-value. And again, it is a two-tailed test. You have to multiply by 2 or compare it to 0.425. Clearly, that area is larger than alpha of 0.25. And you can become the same decision, which is not to reject H0. You can look up the table and guesstimate that with those degrees of freedom. That means degrees of freedom for the numerator and the denominator. Or we can go with the technology. So the p-value method is a two-tailed test. Alpha is 0.25 and F is 2.0269, and that's less than the critical value. The area to the right of the test statistic is greater than 0.25 for two-tailed test. And remember, the p-value is larger than 2 times that. Again, this is rough work from the table. As far as technology is concerned, you put the information in, and it results in the following. So take a look at the test statistic here. It's the same thing we got. And look at the p-value. P-value is 0.214, and it's way larger than alpha of 0.05. It makes sense. If you look at even the graph, it indicates that the p-value is much larger than alpha. By the way, you see the arrow after n1 equals 12. That means I didn't need it for you to see it, but if you go down, it shows you the values of n1 as well as n2. I'm going to look at one more example. This is if you push it down. The only thing that it shows you besides n1, it also shows you n sub 2. There is not much left there. I'm going to look at one more example.
Listed below are stats for the weights in pounds of samples of regular Coke and regular Pepsi. Use the 0.05 significance level to test the claim that the weights of regular Coke and the weights of Pepsi have the same variance standard deviation. And then it has the numbers.
Given information is symbolic, and so you don't have to write it out in essence. So you have n sub 1, n sub 2. They happen to be identical, 36. You have x sub 1, 0.81682, and the other one is 0.8241. Look at S. S is 0.007507 regular Coke, and it's 0.00570001 for regular Pepsi. For the Coke is larger, we choose that as the first group, and we write the test of hypothesis with the first one, H0, sigma 1 equals to sigma 2, or sigma 1 squared equals to sigma 2 squared. Same variance or standard deviation. Either one is fine. And that's the claim, and they are not equal. That would be the one we are looking at. It's a two-tailed test. So you do the test statistic of S1 squared over S2 squared. Remember, you have to square those two numbers. Why do you have to square? Because what you have is just the standard deviation and not the variance. Must be squared. So with that being the case, we end up with 1.7339. Alpha is 0.05. Because it's a two-tailed test, we cut it in half, 0.025, and we use the table of 0.025 with the degrees of freedom of the numerator and denominator, both of them being 36 minus 1 or 35. Note, we didn't have 35, so we chose number 40. Just as an example, again, we can look up the table, limitation of the table. With that being the case, if we put the numbers in, so 1.8752 from the table. If you go with the technology, you get a better answer. And 1.7339 is clearly way into the non-rejection region. So do not reject H0. The claim becomes true, and you know the rest. So do not reject H0. The claim is true. There is sufficient evidence to support the claim of equal standard deviations, or there is sufficient evidence to support the claim that the weights of regular Coke and the weights of regular Pepsi have the same variance.